So we're going to look at these things called related rates, which requires a little bit of implicit differentiation. So when you're looking at one of these, basically they're word problems where lots of things are changing. So pay close attention to what you're trying to find. Pictures are helpful. If you can identify your variables and label your picture, that's really useful. Then you're going to need to write an equation that relates everything that is involved together. And then you're going to take derivative of both sides. And finally, you're going to substitute in what you know and solve for whatever it was you were looking for. So if we are looking at this one, first off, take a minute and read it. And then we're trying to find the rate at which the radius of this circle is changing. So I like to highlight what I'm looking for. I'm going to draw a picture here. So basically we got this pen and its points in the middle and the ink is expanding outward in all directions in a circle. So our radius is changing and that's causing our area to change. So what we're looking for is the rate of change in our radius of our circle, which in terms of our calculus notation is going to be dr dt, because that's the rate of change in our radius over time. Some other info that we have given to us that's involved here is the rate of change in our area of the circle is 0.03 inches squared per second, and that's dA dt, because that's the change in our area over time. So we need a formula that relates area of a circle and radius. So let's do area equals pi r squared. Then we're going to go ahead and take our derivative so that we can get our rates of change involved. So we'll have dA dt equals pi times 2r times dr dt using a little chain rule. If you look at it, we know some of these things. So we know dA dt, and we're going to substitute that in. We also know we're looking for the rate of change when the radius is 1/2. So let's plug that in. And then we can do a little simplifying, multiply some stuff together, and eventually divide by pi to get dr dt is 0.03 over pi, or makes a little bit more sense to think of it as 0.095 inches per second. Okay, so let's look at another one. We've got two cars that are driving towards an intersection, and we're looking for the rate at which they are approaching each other at a specific point in time. So they're speeding towards the intersection. How fast are they approaching each other when car A is 0.3 miles from the intersection and car B is 0.4 miles from the intersection? So it helps if you draw a picture. So I've got my two cars approaching the intersection. That hypotenuse of that right triangle is the distance between my two cars, because distance is always the shortest path measured between 2 points. So let's write down what some of these things stand for. So A in my picture stands for the distance from car A to the intersection. B is similarly the distance from car B's current location to the intersection. And then C is going to be the distance between them. And if you think about it, we are looking at how quickly these distances are changing. We know some of those values, and we're looking for the distance at which the cars are approaching each other. So dA dt is going to be the rate of car A, its speed. dB dt is the rate of car B, and dC dt is going to be what we're looking for, the rate at which the cars are approaching one another. So that is what we're going to eventually be solving for when we set this up. If you think about how we can relate some of this information, well, it looks like a right triangle, so we're going to use Pythagorean Theorem because it relates our distances and our rates that are involved if we were to take its derivative. So taking your derivative, you get 2a times dA dt plus 2b times dB dt equals 2c times dC dt. And then if you plug in what you know, we know the rates for our speeds of cars A and B. Now the key here is that these need to be negative values because my car is approaching the intersection, so the distance from the car to the intersection is decreasing. So that rate needs to be a negative rate of change for both my 50 and my 60. We're looking at the specific point in time when car A is 0.3 miles from the intersection and car B is 0.4, so I can plug those in. Now I need to find C. So if I use a little Pythagorean theorem, the distance at this point in time measured between the two cars is going to be c equals 0.5. I just thought 3, 4, 5 special triangle. And then we're going to solve for the rate of change dc dt. So if you simplify a little bit, you end up with negative 78 miles per hour. Okay, so for this one we've got a rocket which is being filmed by camera. So I'm going to draw a picture. Got my rocket lifting off. I have a camera that is a fixed distance 400 meters horizontally, and that camera is rotating and kind of changing its angle to point at the rocket as it's lifting off and film it. So I'm going to call that angle theta. So things that are involved here, my height of my rocket is changing, so I'm going to call that h. And then I've got angle theta, which is my filming angle, my angle of my camera. So both of those are changing throughout this situation. So dh dt is my rate of change of my rocket, or basically my rocket speed at which it's lifting off the ground. And then I've got my camera angle, the rate at which it is changing, and that's what we're trying to solve for. So for a formula that relates these things, we can't use Pythagorean theorem because we're looking at the angle in our triangle. So we're going to have to use a trig function instead. I know that's your guys' favorite. So we've got opposite and adjacent sides. So I'm going to use tangent is h over 400. So to take my derivative of that, it is a little bit easier if you think of the right-hand side as 1/400th times h. So my derivative of tangent is secant squared, and then chain rule times d theta dt equals 1 over 400 times dh dt. And then if I substitute in what I know my speed of my rocket, so the rate at which its height's changing vertically is 215 meters per second, so I'm going to plug that in. And then I'll have that multiplied by my 1 over 400. If I think about other things, I'm looking for d theta dt. I'm not going to know it. That's what I'm trying to solve this problem to figure out. But I still need some more information because right now I can't solve this for d theta dt if I'm missing secant squared of theta. So I need that, and I can figure it out. So if you think about our point in time that we're looking at, tangent of angle theta at this point in time is h over 400, where h is, says up above, 900 feet, because we're looking for the rate of our camera angle when our rocket has an altitude of 900. So if I plug in 900 for my height, I can find my angle theta at this point in time by doing a little inverse tangent, arctangent. So if you do arctangent of 900 over 400, you can get angle theta. And make sure your calculator is in radians mode, or else this is not going to come out correctly. So use radians, and you should get that theta is approximately, let's see if I plug this in here. It's going to be 1.1526 radians. So if I go back to my problem, I know theta, so I can have secant squared of my angle that I just found. And then I can proceed with figuring out my value for d theta dt, because I can rearrange and solve for it. So easiest way, I think, is to think of that secant squared as 1 over cosine squared. And then if you were rearranging your equation and like solving for d theta dt, I would just go ahead and multiply both sides by cosine squared of my angle, and then you'd just have d theta dt equals 215 over 400 times cosine squared of your angle. Plug it all in your calculator. Yes, we can use calculators on these. And you're going to end up with the rate of change in your angle is approximately 0.0886 radians per second.